Welcome back to our third edition of our blog chat. Myself, Cesar Obediente. Welcome back. We got the pleasure to welcome back again Dr. Mohammed to talk about how his latest paper, CONGA, just won Best Paper in SIGCOMM 2014 in Chicago, and how his paper is implemented in our ACI system and how the benefits are going to influence some of the benefits as load balancing and things like that, and how CONGA, brings all the benefit to the fabric on how to load balance it, and etc. So, we further introduce, I want to thank you again, Dr. Mohammed, to being with us today.
Thanks a lot, Cesar, Chad. It's great to be here again. This work that we did on the paper, the thing that eventually became this CONGA paper is really about this dynamic load balancing mechanism that we built as part of the ACI data center fabric. And I'm happy to talk a little bit about why we did why we actually worked on this, what the motivation for this is, and a little bit about how it works. So looking forward to the discussion.
Excellent, and congratulations for the win.
Thank you. So let me just put up a couple of slides. So you guys see the slides, right? Okay. So the motivation for this work is really that if you look at today's data centers, they require a large amount of bisection bandwidth to support distributed applications. Things like big data applications, HPC, web services that people are deploying, they all have a lot of different components. They're spread across hundreds or thousands of servers, and there's a lot of traffic between the components, what's called sort of east-west traffic within the data center that the network needs to support. And because of this, the traditional single-rooted tree topologies that were the mainstay of enterprise networking for more than a decade are now in the process of being replaced or have been replaced with multi-rooted tree designs. Designs like the fat tree network, or what I'm showing in this picture here, which is a leaf spine design. These new designs are really nice because they basically let you to scale the bisection bandwidth of the network as much as you want by just creating more paths through the topology. So for instance, here, if I need more bandwidth, I can just go and add a couple of spine switches, and I have a network with higher aggregate capacity. Now, this only works really if you're actually able to load balance your traffic across all these available paths to make use of the extra bandwidth. So to really make this design work well, you need to solve a load balancing problem, which is this problem of basically distributing traffic across these different paths. And the way that people do this today is basically throughout the industry, people use what's called eco-cost multipathing or ECMP load balancing, which is a very simple scheme. It basically tries to emulate a randomized load balancing mechanism. So the way this works is every switch will just pick the next hop or pick the path for a packet by taking a hash of the packet's headers of the 5 tuples. So source IP, dest IP, source port, dest port, protocol. Typically, that would be the 5 tuple. You just take a hash of that to pick a path. So for instance, here, if I have a screen flow, my hash might tell me go through spine number 0, the first spine, and another red flow might go through a different spine. So this sort of gives you this randomized way of doing load balancing. And what's good about it is that it does this while preserving packet order. So the packets within a flow won't get reordered because they all take the same path. And that's important for things like TCP traffic because TCP could get confused by packet reordering and think that it's a sign of congestion in the network. So fundamentally, ECMP has sort of two main problems. One is that it can have hash collisions. So this is kind of obvious. So I may have a flow that collides with other flows, even though there are other paths available through the fabric. Another more subtle problem, but perhaps more important problem is that ECMP makes a purely local and stateless decision. This hash-based decision has nothing to do with the actual state of congestion in the network at that instant of time. And this sort of stateless decision can mean that ECMP can perform really poorly if the topology isn't perfectly symmetric. So this is even if there are like a lot of flows in the network, so that the hash collision problem, the sort of the granularity problem of ECMP isn't really there, it can still perform really poorly if the topology becomes at all asymmetric. So to kind of give you a sort of the intuition for why this is, let me just give you an analogy. So imagine you want to go from San Francisco to San Jose, and you have sort of two choices. You can go by 101, and you might go by 280, and you're about the same distance from both, so you're not closer to any one of them. So you try to decide. So ECMP is kind of like making a random decision. You just flip a coin and decide which way to go, 101 or 280, and usually that might actually work fine. But if there's some problem on one of these highways, let's say there's an accident on 101. Now that random decision might be a very bad decision. Half the time you're deciding to go on 101, but later you figure out that, oh, there's actually been an accident here, and there's nothing you can do. So that's kind of what ECMP does. It's oblivious to actually congestion. What we wanted to do was to build a load balancing mechanism that would be congestion aware, that would, in real time, track the extent of congestion on different paths and basically make intelligent decisions based on how much congestion there is on each path.
So Mohammed, if I ask a question, so what you're trying to say is that with this type of load balancing, going back to the analogy between 280 and 101, is kind of you're looking ahead to say, hey, there's a traffic on 101, therefore I don't want to send all my cars to 101. I want to switch those traffic dynamically to 280. Therefore,
That's
now
right.
the network becomes intelligent, and therefore you're not looking at the first hop, how to make that decision. You look at the whole entire system, how to make that decision.
That's right. And actually what you said is a very key point, that to do this, it's not enough to measure congestion on just the first hop, at the switch. This kind of local congestion aware scheme is really not enough. You need to be aware of the end-to-end path congestion. In fact, in the paper that we wrote about this, in this CONGA paper, we go through examples and show how if you make decisions only based on your local proximate links, you might actually end up being even worse than if you had made a stateless decision. So there's sort of examples that show how when you do this and you have TCP on top, the interaction between sort of the two control loops can actually be really bad. So what we do in CONGA or in this dynamic load balancing mechanism is we actually measure an end-to-end path congestion metric. So to kind of give you this kind of the high level idea, it's actually very simple. Once you decide to think of it this way. So every leaf switch or top of the rack switch in our fabric will track congestion metrics on a per path basis from themselves to every other leaf switch. And the key is that these congestion metrics are maintained in near real time. So they really represent the current state of congestion in the network. And then when they have an opportunity to make a load balancing decision, they will just simply always try to send traffic on only the least congested paths. So if there's this accident on 101, before you make the decision, you're aware of it, and you decide you're going to take 280 instead. The key here, though, is how do you actually collect this information? How do we get these congestion metrics? And we do this in CONGA by implementing these extremely fast feedback loops between the leaf switches directly in the hardware data plane. So directly in this ACI basically capable ASIC that we built, we have mechanisms for implementing this very fast feedback loop. And because of that, we get this near real-time awareness of congestion. So let me give you a little bit more detail about how this actually works in our design. So as you might be aware, the ACI fabric operates an overlay that's based on VXLAN. And this overlay is used to virtualize the physical network. And it actually turns out it provides an ideal conduit for implementing these feedback loops that I also spoke about. So the idea of the overlay is when a packet is sent, let's say in this picture, it's sent from host 1 to host 9, the first leaf switch on the packet's path will intercept the packet and encapsulate it with an overlay header, which is this VXLAN encapsulation. The overlay packet is addressed to the destination leaf switch. So here the source is L0 and the destination is L2. And then you simply route the packet across the fabric. At the destination leaf, the leaf will remove the overlay header and send the packet onward. So that's kind of a very, very high level what the overlay is doing. And in CONGA, we leverage this overlay to implement this leaf-to-leaf feedback mechanism. Basically, the way it works is, remember, we're trying to track this per path congestion metric between the leaf switches. So every leaf switch will maintain a table. It's called the congestion to leaf table. It's a table that has a metric per destination leaf and per uplink or per path. So in this example, this is the congestion to leaf table at switch L0. The goal of the feedback mechanism is to populate this table, is to populate the metrics in this table. And the metrics themselves are just these 3-bit values that give you the path congestion. So we get this by basically on every link measuring the utilization of the link. So we have this link by link measurement taking place all the time that gives us a 3-bit metric for the link. And then the metric for a path is just the maximum of the congestion across all of its links. So the way we populate this table is, again, when a packet is being sent, we carry 2 extra pieces of information in the overlay header. We carry a path ID, which the source will set to the uplink number for the packet, and we have this congestion experience field. This is the 3-bit metric for this packet. As the packet traverses the network, on every hop, this congestion experience will get updated. It gets updated based on the actual amount of congestion on the link at that point in time. So by the time that it makes it to the destination, it will have with it the maximum congestion that this packet experienced along its path. So that's the information that we actually want. We want to say for path number 2, this congestion experience metric was 5, but we actually need this at the source because it's the source that's making decisions, for which path to take from L0 to L2.
So Mohammed, real quick, I have a quick question before we get into that, if that's okay. So if I just did this, first of all, we talk about ECMP. A lot of people talk about using spine leaf architectures and just implementing ECMP, and we've already kind of hit on why that's not optimal because of the local functionality. The other thing that comes into play, it seems like, is if I just do an overlay on top of this and I don't have hop-by-hop feedback mechanisms to have this global load balancing functionality and feedback mechanism, then I'm not going to get the benefit either. So really, I have to have hop-by-hop visibility to these to each one of these flow bits to be able to get the feedback mechanisms using these bits. Is that correct? If I'm not mistaken.
You need to measure the congestion basically on every hop of the path. And yes, you do need to basically be measuring this congestion hop by hop. If you have some link that you're not tracking, then you might not see congestion elsewhere, but that path is still congested. So that's right. But in the way that people do this today with ECMP, this whole concept doesn't exist. So as I said, it basically makes a decision that's completely oblivious to what's actually happening in the network. And the assumption that it makes is that all these paths are basically the same. And so all it tries to do is just says, I'm going to randomize across them, and hopefully I'll get an equal split of traffic across these different paths. It might work well if you're actually able to, if the paths really truly are the same, if there's no difference, no asymmetry between them. But as I said, like for example, when there is a link failure, as I'll show, a little bit further ahead, and then the paths may not be the same, and so the decision that ECMP makes is really wrong, and it can hurt application performance quite severely in that case.
Perfect. Thank you.
Yeah, sure. So just to round out this slide, so I need this information at the source leaf, and the way we get this in Conga is we basically piggyback it on packets that are going in the reverse direction. So the switch L2 here will temporarily store the information, and then anytime there's a packet going in the reverse direction, it will pick up the metric from L2 and carry it back to L0 and populate the congestion to leaf table at L0, which is the one that we set out to populate. So this is how we get sort of this information. We end up getting all these metrics for at L0, and now what the leaf switch does is just uses this information to make intelligent decisions about which uplink to use for every packet. And the basic thing, the thing that the most intuitive thing that you want to do is just say, I'm always going to send every packet on the least congested path. So every time I have a packet to send and I'm trying to make a decision across, let's say here in this across these 4 uplinks, I'll look at the table and say, for the destination of that packet, what is the least congested uplink? So it might give me some decisions. If you're sending to L1, send through path number 3. If you're sending to L2, send through one of the first 2 paths. And that's basically what we do. The only catch is that, again, remember, we don't want to cause packet reordering. So that's the thing that ECMP was really good at. It made sure that there would be no reordering for TCP traffic. So we don't actually do this on a packet by packet basis to avoid packet reordering. We make decisions on what's called a flowlet basis. So flowlet is this nice idea. I mean, I'm just referring to a paper from a number of years ago that talked about this idea. It's basically a flowlet is a burst of packets that are separated from other bursts by a large enough gap that you can send one burst on one path and another burst on a different path without actually causing reordering. So the basic idea is, let's say I have 2 paths and the latency of one is D1 and latency of the other 2 is D2. If within the same flow I see a gap that's larger than that delta in latency across the 2 paths, I can send the first burst on one path and the second burst on a different path, and I'm still guaranteed to not reorder packets, because by the time that the second burst is actually makes it to the destination, the first burst must have basically gotten through on its own path. So that's kind of the flowlet idea, and we leverage flowlets in our design. So let me just give you kind of one simple benchmark that we tried. There's a lot more of these experiments in the CONGA paper, and I encourage you to look at those if you're interested. But this is just a benchmark that we set up a Hadoop cluster across 64 nodes. This is a sort of 2 top-of-the-rack switches, 2 spine switches like this, and the Hadoop cluster is across the two top of the racks. And this is a standard benchmark for testing the I/O performance of HDFS. What it basically does is it writes a 1 terabyte file into HDFS and measures the total time that it takes for that job, for that MapReduce job to complete. And what we did here is to get the impact of these link failures, we failed one of those links. So we have an asymmetric topology, like in the picture on the corner there. So this is what we get for the total job completion times across 40 runs of this benchmark. So just to set a baseline, when we don't have any link failures, the average job completion time is around 200 seconds. So that's that green line there. And you can see for CONGA, which is the red line there, that even with the link failure, it completes in almost the same time as it would without any link failure. So the link failure doesn't have any impact because it's able to, CONGA actually is able to move the traffic away from the link failure and balance the traffic accordingly. But if you use a scheme like ECMP, which is what people do today, your job completion times become about 2x larger when a link fails. So you kind of, and this is not a networking metric. This is an actual end-to-end application impact. And the other curve here, on this chart is just it's from the paper. It's another way of trying to address this load balancing problem at the TCP level. It's something called multipath TCP, which I don't want to spend too much time on here. But in the paper we describe why multipath TCP can have variable performance.
So Mohammed, quick question. So now I see that we're kind of wrapping up with time. Well, one thing that intrigued me, and I know you talk about the ACI ASIC, and this is where it gets implemented. We see other vendors out there trying to do similar things, or talk about software as the way of the future, or why you guys did not implement this type of technology, or why cannot be implemented in software?
No, it's a really good question. There certainly are multiple types of designs that you could look at when to get this type of functionality. The big advantage that we get by being able to put this mechanism directly in the ASIC is that we get this very, very fast and accurate reflection of the actual congestion in the network. So at a very high level, what we do in this dynamic load balancing mechanism, in our design or any such design, any dynamic load balancing mechanism, is it needs to implement a control loop. It's a feedback control loop. And in feedback control loops, there's always this challenge of stabilizing the feedback loop. And stabilizing the feedback loop is very easy if you get low latency visibility into the thing that you're controlling. So just to give you kind of a quick illustration of this, this is well understood in the academic literature that these control loops usually need pretty sophisticated control laws to make them stable. So the stability problem is this: basically, if you're trying to, let's say, balance traffic across two paths, and you start from a state like this, where you're congesting one path much more than the other, if I move the traffic too quickly and I don't actually see the impact of what I'm doing, I can overshoot my target. So I can move all the traffic from one path to another path. And then by the time I realize this, it's too late, and then I have to move back. So I can have oscillations like this. And this oscillation and instability actually will degrade the performance of the mechanism. It might be better, again, not to do anything than have a situation where you're oscillating all the time like this. So we get to solve this problem. We get to avoid this issue in our design because that feedback latency that we have between these two leaf switches is very, very small since it's directly implemented in the ASICs. From one leaf switch to another, it might be 5 microseconds across the spine. And so this very fast feedback latency lets us design this very high performance and at the same time very responsive dynamic algorithm. Trying to do the similar thing in software would be very challenging to get this stability to work well, because you wouldn't have this 5 microsecond delay for actually capturing the information, for collecting information. In a software solution, you might have hundreds of microseconds of delay. Or if you're doing controller type solution, it might be in the tens or hundreds of milliseconds, even in an optimized solution. And so that's the advantage that we get by being able to implement this data plane mechanism directly in the hardware.
Got it.
That's great. Thanks, Mohammed, for going through this with us. I think for the people that are going to read this blog, it's going to kind of give them a better understanding of why we did what we did, why ASICs are more optimal for this methodology, and why ECMP and traditional methods aren't really the way to improve performance from an application standpoint, not just from a networking standpoint. So just to kind of summarize, we do flow-let switching, the CONGA load balancing, and the feedback mechanisms using ASICs to have low latency, and within ACI to give the best overall performance for our applications. Is there anything else we missed there? I just wanted to summarize that.
In terms of the data plane innovations that we did in ACI, this load balancing mechanism is certainly, I would say, the most sophisticated thing. But we actually also have mechanisms for dynamically prioritizing certain packets. So that's sort of an orthogonal feature, if you will, from this load balancing, where the challenge that we're addressing there, I can give you the big picture in a couple of minutes, is just that there's a lot of interference that happens in these networks between packets of large flows, what are called elephant flows, and packets of mice flows. So elephant flows have a lot of bandwidth, and they can easily congest the port or the links that they're communicating through. Mice flows have very small bandwidth, but they really need a very low amount of latency. So they're latency sensitive. And what happens regularly with standard TCP traffic is the large flows will build up these very big queues that the mice flows then get blocked behind, and it adds significant latency and hurts the mice flows. One of the things that we developed as part of ACI is this dynamic packet prioritization mechanism where the hardware will automatically detect that certain packets belong to mice flows, and it will actually give them priority by putting them in a separate queue inside the switch, so they can kind of bypass the packets of the elephant flows. And this, again, we've seen gives a lot of benefit for these short latency sensitive flows, and can significantly reduce the latency through the network. Sometimes it's as dramatic as more than 50 or even like closer to 60 to 80% reduction in actual average latency for short flows when they're competing with large elephant flows at the same time.
So Mohammed, this is also implemented on the ACI ASIC. Can you explain on a high level how actually we're monitoring for these small flows versus big flows? Are we looking at just the starting on a flow when it comes in, and then we monitor that flow because we suspect that, because of the TCP window sizing?
So the basic idea is that at the start of these flows, if a flow has been idle for a long amount of time, the initial packets of it we assume it's a mice flow, and we start prioritizing it, and then but very quickly, if we detect that it's actually an elephant flow, we'll stop prioritizing it. So we essentially prioritize the beginning of all the flows, and this gives us again a significant benefit for the things that are actually small, because their packets will get queued in these higher priority queues, and they won't get sort of trampled on by the packets by the majority of packets of the elephant flows.
So we're taking that, we're prioritizing the flows that need to be prioritized so they can have their lowest latency. We're putting the longer flows, the elephant flows, in a different priority levels because they're not so much latency sensitive. They're going to be longer lived. We give them the different priority. Then we look at all the feedback mechanisms. We look at the congestion across the entire system, and we do load balancing across that to make sure that there's no packet reordering and all that.
That's right. So the dynamic prioritization, kind of if I was trying to give you a real real world sort of use case for it, imagine you have something like a network that concurrently is running some big data type workload like Hadoop, and at the same time you have something like Memcached, which is this very latency sensitive application that's sharing the same network. So with our dynamic packet prioritization, the majority of your Memcached traffic automatically will get better treatment through the network because we detect that these are these mice flows, so you'll see a big performance boost for the Memcached, and you'll see consistent performance still for the Hadoop workloads that you have.
That's excellent. Well, thank you, Mohammed, for spending the time. This has been very informative to myself and Cesar, and I'm sure to all of our listeners and readers of the blog. And we look forward to the next one that we do with you to get more details around ACI and more enhancements that I'm sure you're working on that are going to come to the ACI fabric. So again, thank you for your time today, and we look forward to the next one. I'll talk to you soon.
Happy to be here. Thank you, guys.